So let's have a look at how we can calculate the pH of a weak acid, and we're going to look at how it's done at A level, which uses a couple of approximations. We'll just talk a little bit about why they work and when they don't work. So first things first, it's an equilibrium, so there's the equilibrium at the top, if you calculate an equilibrium quantity, then you usually start with, well, what do we put in? So let's start with the known quantity or concentration of the acid, we start with no products, and gradually that reaches equilibrium. I've called the initial concentration of HA there, so let's say we were adding solid citric acid to water. We'd know the amount in moles that we're adding, and we'd know the volume, so we could work out the concentration that way. So that I've called that HAAQ INI for initial. What we're going to do is we're going to do a little bit of thinking. We're going to say, right, at equilibrium, that's going to be a different concentration, which I've called HAAQ equum, the H plus concentration is going to be obviously larger. We have made H plus equum, which stands for equilibrium, and the A minus as well. So the first thing that we can see from the equation is that every one molecule of HA that dissociates is going to produce one H plus proton, basically. And because of that, we know that the HA concentration at equilibrium is actually equal to the initial concentration minus the concentration of the H plus, because everything that's been made into H plus has been made into H plus in a 1:1 ratio from the original HA. So we can say the same number of moles of H plus has been made as HA moles have been used, and that's why we can say the equilibrium concentration of HA is the initial HA concentration minus the H plus concentration at equilibrium. And that's all well and good, because we know that pH will measure H plus concentration, and so we've got two things that we know. We know the initial concentration at the when we set up the equilibrium, and we know the H plus concentration. So what do we do with the A minus? Well, at this point, our Ka looks like this. We know that at equilibrium, this is what it would look like. We can substitute in the term HA at equilibrium for the initial HA minus the H plus at equilibrium, and that gives us this. So we can calculate all of the things there apart from A minus, and this is where we're going to make an approximation. And we're going to make the approximation that H plus concentration is equal to A minus concentration. Now this seems logical because for every one H plus you make an A minus. Every time HA dissociates, you get one of each. So why is it an approximation? Well, because water also dissociates, and it dissociates into H plus. So there's a tiny bit of H plus being produced just in the water itself. So the concentration at equilibrium of H plus is actually very slightly greater than the concentration of A minus, because of the additional H plus from the water. So really, H plus concentration is the H plus of the acid and the H plus of the water. We could actually calculate that because we can work out what the H plus of concentration in water is, but we don't really have to, because if we have a weak acid and it's pH 4, here are some values here, you might have a concentration of acid of 10 to the minus 4. At this point, the water in a normal room temperature situation is something of the order of 10 to the minus 7 moles per decimeter cubed. These are in moles per decimeter cubed, and that means that the actual concentration of H plus is going to be 1 0.001 times 10 to the minus 4. So you can see there's not really much difference in that calculation. And actually, when we're talking about how many decimal places away it is, how often do you write something at A level 2? More than 2 decimal places. So it works as an approximation. There's a tiny bit of error there. Sometimes it doesn't work. So let's compare that to something which is a very, very weak acid. Let's say it's pH 6 in the same conditions, and the concentration of acid would be 10 to the minus 6, and the water would still be same conditions. We'd be looking at 10 to the minus 7 moles per decimeter cubed, and therefore we would now have the H plus concentration being 1.1 times 10 to the minus 6. Now that's a 10% error, isn't it? We're going from 10 to the minus 6 to 1.1 times 10 to the minus 6. We've got 10% more. And so that's when it starts to become an issue. You can use this approximation safely for anything. Ideally, the lower the pH, the better it's going to be, basically. But you certainly wouldn't want to use this approximation for anything above pH 6, because you're starting to get into, above 10% error is never a good idea. We can use it for relatively strong weak acids. So, or we can use it for quite concentrated weak acids as well. So we can approximate that Ka is equal to the concentration of H plus squared at equilibrium divided by the HA concentration initially minus the H plus at equilibrium. So far so good. So this can be simplified further. We can come on to another approximation here, and that is that the concentration of HA actually doesn't change much. So it's effectively equal. So we know that some of it has been used up, otherwise it wouldn't have dissociated at all. But actually, if you look at the Ka values, you'll see for quite a substantial number of weak acids, the Ka value is actually very small. And so the equilibrium is shifted actually quite over to the left-hand side. So HA is in vast quantities compared to H plus and A minus. So we can approximate that actually it makes no difference that some of it's dissociated, because the amount that's dissociated is so small that it doesn't really matter. For example, if we have 1 mole per decimeter cubed solution of initial concentration, and the Ka is approximately 10 to the power of minus 10, then I calculate that the H plus concentration would be something like 10 to the minus 5 moles per decimeter cubed. So when you write that to 3 significant figures, 4 significant figures, you end up with the same number as you did before, with the HA initial and the HA equilibrium are effectively the same until you get down to 1, 2, 3, 4, 5 decimal places. And that's a tiny percentage error, and that's okay. We don't mind that at all. So when it doesn't work so well is when you have a stronger weak acid. So when the acid dissociates more, we end up with a bigger effect of ignoring the amount of H plus which is used up. So let's say that Ka is 10 to the minus 2 instead. Let's go to the other end of the scale. We have H plus in this case would equal, well, it would be approximately 10 to the minus 1 moles per decimeter cubed. So again, we end up with about a 10% error there. So yeah, we can, depending on the concentration of H plus caused by dissociation, we can make this approximation if we have something which is sufficiently concentrated but also very weak. If we have something which is a little bit stronger or extremely dilute, then this doesn't work. So assuming that it works, we end up with an approximation which is H plus concentration squared at equilibrium divided by the initial concentration is approximately Ka. And from well, I mean, at A level, this is basically what you use. But the be aware that there are limitations, because you do need to understand why this is limited and in what cases it can't be used.